Hello class, good evening. How's everything going with you this week? Thank you for saying hi. Okay, so let me take a picture of the attendance, then we start the new chapter today. We're going to start chapter 5. In fact, we are going to finish chapter 5 today. Chapter 5 only has 2 sections. The first section is about the probability distribution table. Second section is a specific discrete random variable distribution is called binomial distribution. So 2 main things today, okay? So let me go to my OneNote and we're gonna get it started. First, we're going to learn today is a random variable. What is a random variable? A random variable Yeah, I probably use R dot V dot to represent random variable. And what is a random variable? Random variable is a variable that has a single numerical value determined by chance for each outcome of a procedure. You might remember procedure, right? Procedure is a probability experiment. Toss a coin is a procedure. Rolling a die is a procedure. Rolling 2 dice at the same time is also a procedure. Yeah, something like that. And probability experiment is a procedure. And we know the concept of the outcomes of procedure, right? For example, if we toss a coin, the procedure has 2 outcomes. The first outcome is getting head. The second outcome is to getting tail. The 2 outcomes, getting head and getting tail, are not numerical. But we really want to make them numerical. You see what I'm talking about? So mathematicians or statisticians, they brought in random variable to numeralize the outcomes of a procedure. This is a very important milestone in the development of probability. Because of random variable, we are able to use real analysis to study probability. And it kind of like open a window of a bigger world after that. You see what I'm talking about? It's very important. So random variable is used to numeralize the outcomes of a procedure. The outcomes of a procedure sometimes are numerical. For example, rolling a die, the outcomes are numerical, right? 1, 2, 3, 4, 5, 6. But most of the times, they are not numerical. Yeah, tossing a coin, the 2 outcomes, head and tail, they are not numerical. But we really wanted to make them numerical, then we can use other mathematical tools to study them. And that's when we need a random variable. Okay? Notation of random variable. We use capital letter X, capital letter X to represent random variable. Okay? For example, we toss a coin. There are 2 outcomes. And we can let X be the number of a head. Okay, then with this random variable, we are able to numeralize the outcomes of the procedure. Let me show you how. So we toss a coin. We toss a coin. If we get a head, then I'm gonna use a colon here. If we get a head, then the number of head is 1, right? So x equals 1. You know that? So the event getting a head is the same with the event that x equals 1. So if we toss a coin and the result is a tail, that means the number of head is 0, right? So the event or the outcome getting a tail can be represented by x equals 0. Yeah, so this is how we numeralize the outcomes for procedure. And let me know, does that make any sense? Or you can also read the definition here, the formal definition. My explanation hopefully help you to understand the concept here. A random variable is a variable that has a single numerical value, has to assume a specific numerical value, determined by chance for each outcome of a procedure. Basically, random variable is used to represent the outcomes and assign each single outcome a specific value. Does that make sense? Let me know. Yeah, random variable is very important, and we use capital letter X to represent random variable. Yeah, okay, thank you, Charlene. Yeah, that means I was clear about the explanation, right? Yeah, that's what is a random variable. And we have two types of random variables. The first type is the discrete random variable. Yeah, let me just write a word, random variable. And second type is called a continuous random variable. Today we learn discrete. On Thursday we learn continuous. So what is a discrete random variable? If the random variable x only has a finite number of values, or x could assume infinitely many but countable many numerical values, then x is discrete. In contrast, if random variable x could assume any value in an interval, for example, from 0 to 1, any value in this interval, then x is continuous. Let me give you some examples. Let's say you survey households with 3 children, and you let x be the number of girls in the 3 children. Then help me to find all the possible values for x. Help me to find all the possible values for x. So you randomly select a home with 3 children. And is it possible there's no girl, all the boys, right? All 3 are boys. And is that possible there's exactly 1 girl, 2 boys? Or exactly 2 girls, 1 boy? Or all the 3 children are girls, right? Do you see that x assume finite number of values in this case, right? So x in this case is discrete random variable. X here is a discrete random variable. Does that sound good? Yeah, this case is discrete. DRV, discrete random variable. If the variable x assume a finite number of values, then it is discrete. And another example, let's say we toss a coin. And we use random variable x to be the number of tosses before getting the first tail. Okay, let's see what are all the values x is could possibly assume. Okay, you toss a coin, and x here represents what? The number of tosses before we getting the first tail. Yeah, we keep going, we toss the coin. If we see the first tail, then we stop. If we don't see a tail, always head, and we continue. All right, yeah. So is it possible we get a 1? Yeah, it's possible we get a 1. We only need to toss one time and get a tail, right? So x equals 1. Or the first time we did not get a tail, and second time we get a tail. So we need 2 tosses to reach that goal, right? Or we can try 3 times, the third time we get a tail. Or 4, or 5, or 6. Technically, I know you might think, really? Yes. Technically, x could be, we could keep going, never get a tail. Do you see what I'm talking about? Yeah, how big that chance is, it depends on what the coin, maybe the coin is not fair, right? Yeah, maybe the tail side is very heavy. Yeah, so always give it head. That's possible, right? So in this case, do you agree that x could assume all the natural numbers? So x assume infinitely many, but countable many of values. In that case, the random variable still DRV, still discrete random variable. Yeah, only those 2 cases. Either random variable x assume finite number of numerical values, or x assume infinitely many but countable number of numerical values. And in those 2 cases, the random variable is discrete. Yeah, let me know. Yeah, mainly so is counting. So here x is used to count. Okay, x is used to count. Am I clear about the definition, the meaning of discrete random variable? Yeah, okay, thank you. And what about continuous random variable? Can I give an example for that? Yes, it's pretty straightforward. Let's use x to represent the temperature. Temperature. How about in Fahrenheit? Yeah, because we use Fahrenheit in this country. Yeah, from today 8 a.m. to 8 p.m. Right? In that case, x is a continuous random variable. Continuous random variable. Suppose the minimum temperature today, what is the, let's say, I'm not sure, maybe 68 degree, right? And 8 p.m. right now, '79. Yeah, just let's pretend is 78 later, just in like 20 minutes. All right. So the temperature x, the x could assume any value between this interval, right? Because when it changes, when the temperature changes, cannot jump. It has to change gradually, continuously. In this case, x assume any value in an interval. When the variable could assume any value in an interval, that random variable is a continuous random variable. So normally, the continuous random variable is used to measure. Okay, yeah, normally, not absolutely, depends on the situation. Yeah. So discrete random variable normally is used to count, and a continuous random variable is normally used to measure, like a weight, like a height, temperature. Yeah. In those cases, the random variable is used to measure, then that random variable is continuous random variable. Let me know, am I clear about the difference between the two types of random variables? They are used to represent or numeralize. Awesome, thank you. Numeralize the results or outcomes of a procedure probability experiment. Okay, we have more questions to practice, okay? My plan today is do not go too slow because we have 2 sections to cover. So here we have the definition for discrete and a continuous random variable, okay? Yeah, a discrete random variable has either a finite or a countable number of values. It's same with what I said, but it's actually not very complete, or infinitely many but countable number of values. And a continuous random variable could assume any value in an interval, but here it says has infinitely many values associated with measurements. To be honest, the definition on my lab math is not the best. I think I give you a better version of the definition. Not just infinitely many. Discrete random variable could assume infinitely many, but is countable. Continuous random variable assume infinitely many, but uncountably many values. Basically, is any value in an interval. In an interval. Okay, so for discrete random variable, we're gonna study discrete random variable today. We focus on the probability distribution table of a discrete random variable. Okay, yeah. So next up, once we know what is a discrete random variable, we are going to look at the definition of a discrete random variable table. Yeah, sometimes say table, just discrete random, just the sorry, I said it wrong. Sorry, probability distribution table. Okay, probability distribution table. Okay, let me give you the definition. Probability Let me restart my OneNote. It just crashed. I think I'm still sharing. I'm recording, so all good. We have just learned what is a random variable, what is a discrete random variable, and the difference between discrete random variable and a continuous random variable, right? So next up, we are going to learn a very important definition. It is called the probability distribution. It is a table. So sometimes I would say probability distribution table. Okay, right here. Probability.
Where'd she go?
Yeah,
Is
no idea.
Is the probability distribution table. Any questions so far?
Your screen went off and you disappeared, so we didn't hear anything.
I disappear.
Yeah, you weren't on there.
I am sharing for sure.
It just came back on.
Okay. Yeah, how about now, guys?
Yeah, it's working now, but for a second, yeah, it was just us on this page, and you weren't hosting anymore. It's like it
Oh,
kicked you off or something.
sorry about that. My OneNote crashed. I had to restart it. Are you able to see my OneNote right now?
Yes, we can.
Okay, awesome. Yeah. So now we are going to learn a very important definition concept. It's called a probability distribution table. We use the table to study discrete random variable. For continuous random variable on Thursday, we are going to learn a different tool. But for discrete random variable, we use the tool of probability distribution table. Okay? Yeah. So what does a probability distribution table look like? What a kind of table can be used as a probability or can be could be a probability distribution table. So here is an example. Probability distribution table very similar with frequency distribution table. Okay, not the grouped one, is the regular one. So it has two columns. The first column, we have all the possible values for that discrete random variable. And second column, we have the corresponding probability for each value the random variable x assume. So let me explain. So when x equals 0, again, you see this as an outcome, right? Yeah, x equals 0 is an outcome right now, or event, a result of the procedure. So this means the probability that x assumes 0 is 0.029. The probability that x equals 1 is 0.154. The probability of x equals 2 is 0.317, and so on and so on and so on. The probability of x equals 5 is 0.029. You see that? Yeah, that's how do we understand the two columns and the relationships between the two columns. As you can see, the title, technically, this is supposed to be bigger x, okay? Yeah, even the book, sometimes they do not differentiate, which is incorrect. They're supposed to make this x bigger. They're supposed to make this x a capital X. Because here, this x is a small x, lowercase, is different. Lowercase x is the value of the random variable. Capital letter X represents the variable itself. Okay, so very important. The second column, because the second column we have probabilities. Those probabilities must be between 0 and 1. Okay, not 0. If the probability is 0, then you would not have that row. You see what I'm talking about? Means x does not assume that value. So it has to be strictly bigger than 0. It's not equal to 1 either, because if probability equal to 1, then the variable is not random anymore. It's certain to occur. So the probabilities, those probabilities in the second column, they have to be strictly bigger than 0 and strictly less than 1. That's the first condition needs to be satisfied in order to be a probability distribution table. The second condition is all the probabilities in the second column, they must add up to 1. Think about, does that make sense? Because all the values that x could assume are 0, 1, 2, 3, 4, 5, and those are their corresponding probabilities. And since those are outcomes, right? X equals 0 is an outcome, x equals 1 is an outcome. So all the outcomes, they are disjoint. Remember disjoint. So all their corresponding probabilities add up to 1. They should add up to 1. Does that make sense? The probabilities have to add up to 1, 100%. Because in any procedure, the result either is this outcome or this outcome, at least one of the outcome occurs, right? So altogether, they add up to 100%. Let me know if you understand the two conditions. Yeah. In order for a table to be a probability, okay, no questions. Okay, awesome. In order for the table to be a probability distribution table, those two conditions must be satisfied. All right? Yeah, when you work on the MATLAB math problems, and you would be asked to determine that, and those two things is to check. All right, let's this question. Yeah, what table describe what kind of random variable we have here? 5 males with an X-linked genetic disorder have one child each. Seems very complicated. The random variable X is the number of children among the 5 who inherit the X-linked genetic disorder. Determine whether a probability distribution table is given. If a probability distribution table is given, find its mean and standard deviation. If a probability distribution table is not given, identify the requirements that are not satisfied. Okay, look at our table, the 2-column table. Check the 2 conditions, yeah, and then select from the A, B, C, D, E. Are we having a probability distribution table? Yeah, look at all the probabilities. Are they between 0 and 1? And then add them up. Do we have a sum? Do they have a sum exactly equal to 1? And let me know. You have your calculators? Yes? Okay. Yeah, exactly. Thank you, Melinda. Yeah, if you try it, take your time. You'll see. Yeah, obviously, all the probabilities between 0 and 1. And if you add them up, use your calculator, you would have 1 exactly. So yes, the table shows a probability distribution. Okay, let's see if we have any questions. Yep, very good. Thank you, Leah. And part B, find the mean and standard deviation. Let me firstly show you how do we find the mean manually and how do we find the standard deviation manually. Let me explain the process, and then I show you how do we do that using the calculator, okay? To find the mean, mu. So by the way, the main difference between frequency distribution table and a probability distribution table is frequency distribution table is for a sample, mainly for a sample, and the probability distribution table is for a population. The random variable X here represents the population, okay? Is population, represent the population, or a feature of the population. So this is about population. That's the reason the mean, we do not use X bar anymore, okay? Because X bar is a sample mean. Instead, we use mu. This letter, mu, is longer leg, kind of like a U, but it's not use mu. Yeah, we use that to represent. Mu is the population mean. Yeah, here represent the mean of X. Yeah, of X, the random variable. How do we find it? Manually. This is how. We are going to add up the product of the 2 quantities in each row. Okay, you'll see. So the first row, value is 0, multiplied by corresponding product, right? We know the 0, but I just read it there. And second row, we have 2 numbers, right? The value of the X and the corresponding probability. So we're going to have 1 times is the corresponding probability, 0.154. And you probably know how to continue, right? And then the next row, we have 2 times 0.317. And the next row, we have 2, oh, not 2. Next one, we have 3 times the corresponding probability, 0.317. Plus next row is 4 times 0.154 plus, and then 5, the last one, 5 times is the corresponding probability, 0.029. Remember the correct order of operations. We must find those products first, okay? Find those products first, and then add them up, and then add those products together, okay? And the value would be the mean, would be the mu that we are looking for. All right, the mean of the random variable x. You know, how do we call the mean of the random variable x? Is actually expected value of x, which is mu. Okay, let me know, am I clear about how do we find the mean of the random variable manually? Is the formula clear? Or does that make sense? Does anyone know where I can find the recordings of our? How about you email me that? I'll tell you. Yeah, I'd prefer you ask that question later. Okay, so yes, I'm clear about the how do we find the mean, right? Well, now let me show you how we find the standard. Remember, for sample, we use S to represent the sample standard deviation, right? Yeah, but we are talking about a population. X is a population. So we use a different notation. Sigma here is the population standard deviation. Okay, so from now on, you need to start to know those notations. And mu is the population mean. And sigma is the population standard deviation. By the way, Riley, since you asked the recordings, very, very long time ago, probably the beginning of the semester, I sent you a short. In that short, I shown you how do we find the recordings. Probably around, it's the first week. I sent you an email. There's a video there, very short. Okay, so how do we find a population standard deviation? This is the process, okay? It's not exactly the formula. I'm going to just show you the process. Firstly, we want to find the deviation of each value from the mean. Suppose we know the mean already, okay? 2.5, I have it here anyway, so 2.5.
Professor, I have a question.
Yes, please.
In the green, did you multiply? Is that why it's in parentheses, like 0 times 0.029 and then plus that?
Yeah. So
Okay.
the parentheses means multiply. That's a very good question. That's an algebra question. For example, this means 2 times 3, right? This is also means 2 times 3. But this also means 2 times 3. This actually also means 2 times 3. Or this also means 2 times 3. So with the parentheses, that means multiply. So we want to multiply the value and its corresponding probability, and we get 6 products, right? And then we add up those products. We should have 2.5. We don't have time to check that, but the answer is 2.5. So to find the standard deviation, we firstly need to find the mu, which is 2.5. And then we're going to find this. And we are going to find out the deviation from the mean. Use the first value minus the mean and square it. And use the second value minus mean, square it. Continue. Luckily, we only have 6 values. Yeah, just give me a little time, and then we are doing the calculator thing. So you use each value of x, right? Yeah, x only assumes 6 values, 0, 1, 2, 3, 4, 5. Use each value to minus the mu, and then square it, and then add them up. Okay, and then you know what do we do? We take the square root, and that would be the sigma. All right. Oh, sorry, I missed one thing. Multiply by the probability. My bad. So I don't really use this method much. Multiply by the corresponding probability. This by 0.154. You multiply this by 0.317. Multiply this by 0.317. This is 0.154. This is 0.029. Yeah, let me redo it. I'm so sorry. So firstly, we use each value to minus the mu, and then we square those differences. Okay, and then we multiply each square by its corresponding probabilities, and then we add them up, and then we take the square root, and then we have the sigma. I'm not gonna do that, okay? It's very time consuming. In case you don't have a TI-84 calculator, that's how you do it. Keep me updated on that. If you need help with the process, email me. Is there an easier way? Yeah, now I'm gonna show you. The reason when we firstly do sample standard deviation, I use the formula because we at least have to use the formula a couple of times to understand the concept. But after that, I would use the calculator. Okay, give me a few seconds to share my camera. Bear with me. Share camera, HD camera. Give me a little bit of time. Can't access, really? Let me reconnect. Let me try again. Let me try to connect my camera again, okay? Can you see my camera? I mean my calculator? No? Okay. Can you hear me? Okay, awesome. So sorry. That's why I don't really do this often, because when we switch, something messed up, I have to reload it. Okay, guys. When we are given, what are we doing right now? When we are given a probability distribution table for a discrete random variable, we often are asked to find the mean and the standard deviation of the variable. How are we going to do that? very quickly by using TI-84 calculator. This is what we're going to do. This is what we're going to do, okay? Go to stat. Okay, firstly, we need to turn on the calculator. Firstly, turn on the calculator, okay? And then we go to stat. If you have a TI-84 calculator, do it with me. Stat, and then edit, confirm edit. To save time, earlier before we start a class, I already enter the values in column 1, as you can see, 0, 1, 2, 3, 4, 5, right? And I'll also enter the corresponding probabilities in column 2. Yeah, I'll give you a little bit of time, you do that yourself. Okay? Yeah, enter the values. Basically, list the values of x in column 1, L1, and the corresponding probabilities in L2. I give you a little bit of time for that. Okay? Do you want me to read the probability? So the first list, you enter 0, enter 1, enter 2, enter 3, enter 4, enter 5. And then the second column, in list 2, you are going to enter 0.029, confirm, 0.154, enter, 0.317, enter, 0.317, enter, 0.154, enter, 0.029, enter. Okay? And then once you have the 2 columns ready, you go to stat, and then this time you go to the right one time, calc, and then confirm the first item in the menu, which is one variable stats. Okay, here, very important. You're gonna enter L1 for your list because your values, the values of the random variable x is there. So the list is L1. And since we put the probabilities in L2, you're gonna have to fix the frequency list, the second one, as L2, okay? And then you calculate. I did not get my values in before you went on. Can you show again, please? Okay. How about let me just say it. Can you take notes? So the first column, x, assume possible values for x are 0, 1, 2, 3, 4, 5. Okay, that's the first column. The second column, we have 6 probabilities. The first probability is 0.029. Second probability is 0.154. Third probability is 0.317. Next probability is also 0.317. Next probability is 0.154. The last probability is 0.029. So those 6 probabilities correspond to the 6 values, okay? 0 corresponds to 0.029, 1 corresponds to 0.154, 2 corresponds to 0.317, 3 corresponds to 0.317, 4 corresponds to 0.154, 5 corresponds to 0.029. You get it? Okay, very good. Okay, awesome. So now you're gonna go to stat again, but this time go to calc. Stat, calc, and then run one variable stat, the first item on the menu, and you will see this one, right? And the list gonna be L1. Your frequency list is gonna be L2. By the way, you are not gonna see probability list because they just use frequency list to represent all other similar thing. And then you move to calculate and you calc. And let me know, do you see those? Do you see that? Yeah, do you see mu? You're not gonna see mu, by the way, okay? But you see x bar. X bar is our mu. Yeah, so be flexible. It's not very exactly the same notation, but you know x bar here is the mean that we are looking for. So 2.5, right? And do you see S sub x? You do not see S sub x, right? Because this is about the population, but you would see sigma sub x. Sigma sub x is the standard deviation of the random variable we are looking for. Okay, two things. The first item, x bar, that's the mu, that's the mean we are looking for. And then go down, the last second you see sigma sub x, that's the standard deviation of the variable. Am I clear about that, guys? Yeah, knowing this method, then you don't struggle when you do your homework. Awesome, awesome. I think I'm clear, right? Okay, so I'm gonna, yeah.
Sorry, that it's not showing up for me. Like it is only saying 0.029 must be an integer.
0.029. So which step you are on?
So I'm on that I'm on that part where it says list L1 and then the frequency list, and then I put L2, and then I entered it, and it's not showing any of that.
Do you have your values in L1 and probabilities in L2?
Yes, it's so L1 is the 0, 1, 2, 3, 4, 5.
L2?
Yeah. L2 is 0.029, 0.154, 0.371. Or
double check the values. So we should have 0.029, 0.154, 0.317, another 0.317, 0.154, the last one 0.029. You have the same thing?
It was 0.317, right?
0.317, yeah. We have two of those.
Yeah, it's in there, right?
Did you do the list frequency correct? Did you do like the ones on the screen right now, Leah? Did you use the L1, L2 right there to calculate?
Yes, yeah, I went to stat and then calculate, and the first one variable stats. And then list is L1, and then frequency list is L2, and I went second L2. And then it just says, I'm using, it's probably because I don't have the actual TI-84 calculator. I'm using the app on my phone. Because I usually use it for the assignment, so that must be it. It might not.
You wanna try it on a actual TI-84 calculator.
Yeah.
You can
usually
use
the app works it works fine, but I guess there are some limits to it.
What the sample size is 1? It says sample size is 1. N is 1. Just ignore that. I don't know why it's 1. So we don't have a sample, by the way. By the way, we do not have a sample. Yeah, that's a very good question, Melinda. We do not have a sample. We only have a population here. Oh, okay. You know what? N here is not sample size. N here is the number of trials. Number of trials. You only do the experiment one time, and variable x represents the possible values for the outcomes. You only did the experiment procedure one time. So N here is not sample size. It has different meaning. Very good. It's good that you noticed that. Okay. Yeah, let me go back, okay? Yeah, as I said, we want to finish 2 sections today, so we cannot just spend too much time on this. Let me go back our OneNote. I wish the technology is better. I wish my personal device is better. But this is the best I can do. I have my personal laptop, personal camera, documentary camera, everything. It's just when we have too many things in a virtual classroom, sometimes when we switch between the modes, it just crash. Okay, so this is a good problem, and many other problems are similar. Now I'm gonna find a problem that you might have trouble, because we need to cover at least one, and you'll know how to do that when you go to your homeworks. Let's do okay, let's do 18, number 18, okay? Number 18. In a States pick 3 lottery game, you pay $1.43 to select a sequence of 3 digits from 0 to 9, such as 377. If you select the same sequence of 3 digits that are drawn, you win and collect $361.13. Complete part A and part E. So this is help us to construct the probability distribution table for the given variable, okay? Firstly, how many different selections are possible? So the lottery is a pick 3 lottery, means this is the process. You're gonna pick a digit. Sorry, one node is crashed. Let me do it again. Let me
Hey, Professor, we're not able to hear you talking. Can you hear us, or can you hear me?
back to the OneNote. Sometimes it automatically muted me. You should be able to hear me now, right? Okay, very good. Sorry about that. Yeah, so how do we play the lottery? How do we play the pick 3 lottery game? The first step, you pick a digit in the first cell. You have 10 options because you can choose any digit from 0 to 9. And second step, you do the same thing. The third step, you do the same thing by the multiplication counting principle, the fundamental counting principle. do we have 1,000 different options, selections? Do you agree on that? Yes? Okay, awesome. And then what's the probability of winning? If we win, that means the selection exactly equal to the one that is winning, right? So that's the numerator. There's only one winning selection. And the denominator gonna be the total number of selections. So very important here. The probability needs to be an integer or a decimal. So if you enter 1/1000, the system will mark it wrong. You have to convert the fraction to its equivalent decimal, 0.001. Are we good with the second part? Yes or no? The probability is classical. You probably say yes. Okay. Let me double check if you have any question. Okay, very good. And part C, if you win, what is your net profit? You know, profit is a profit. Net profit means profit, okay? Yeah. So it emphasizes net profit means it's not your revenue. It's not your revenue. Because you have to remove your cost from the revenue to get your profit. So if you win, you're gonna collect $361.13, right? But you paid $1.43. That's your cost. So this is your revenue. This is your cost. The difference is gonna be your profit. All right. Do the math. Your profit is the difference of that. You have $359.70 profit. Okay, profit is profit, is where the net profit. Is that clear, part C? If you win, your profit is $359.70. This part is to remind you, your profit is not $361.30. You have to subtract your costs from the collection, the $361.30 to get your profit. All right? Yeah, because we are learning mathematics, and sometimes we ignore, the actual business formulas. So part D, find the expected value. Yeah, I mentioned what is expected value if you heard me earlier, but let me explain what is expected value. Expected value is the mean, okay? Is the mean, yeah, is the average. Expected value is the typical value you are expecting the verb X to assume in one trial. So basically it's the mean, the average, or the typical value. Okay, so in order to find the expected value of a random variable, here is discrete random variable, we need to make a table. Okay, whenever you need to find the expected value of a random variable, you need to make a table. Let me show you how do we make a table, okay? You need to make the probability distribution table. So the first column, I actually make a 4 column, but only the 2 column in the middle, the yellow one, is the probability distribution table. The other 2 columns help us to organize. Yeah. So I would label this as cases. Okay. So we have 2 cases. When you buy a lottery, we only have 2 cases. Two cases. Either you win or you lose, right? That's only the 2 cases. Yeah. So X here gonna represent what? X here is gonna represent your profit in dollars, right? Questions? Let me see. Oh, no problem. Oh, okay. It's not about me. Okay. So random variable X here, you need to know, is the profit. Okay. Profit. So when you win, your profit is in part C, is $359.70. Question. Yeah, don't type, just tell me. It's faster. Unmute yourself and tell me, When you lose, what's your profit? Don't type. Just tell me.
0.
Or
No.
negative.
Yeah, negative 1.43. Awesome. Very good. Thank you. Yeah. So tell me, what's the probability of winning? Look at the part B. What's the probability of winning? Yeah, just tell me.
0.001.
Yeah, exactly. Oops, that's too thick. 0.001. Yeah. And what's your probability of losing? Complement.
0.999.
Awesome. Perfect. Okay. So the yellow part, guys, the yellow part, if I frame it, that's the probability distribution table of the random variable x, right? Yeah, random variable x here is the profit. Why the profit is discrete? Because the smallest unit is a cent, right? It's not continuous. It's not like a temperature. It is still a count. Yeah, money is discrete because the smallest unit is a cent. Okay, so we're gonna do one more column. That column is going to be the product. Okay. So how are we gonna do that? We're going to multiply the profit with the probability. So 359.7 multiplied by 0.001. Yeah, use your calculator. And here we also have a negative 1.43 multiplied by 0.999. Okay. Yeah, let me do the calculator. Let me get it a product quickly. So we have 359. Oops. 359.7 359.7 times 0.001. That is 0. Yeah, actually, we don't have to do that by using calculator. Just move the decimal point to the left 3 times. 0.3597. And this one is negative 1.43 times 0.999. It's negative 1.42857. Okay, and then you are going to add those two things up. Add this one and this one together. Be careful, the second value is a minus. Okay, yeah, minus. So let me know what you have. Do you have negative 1.06887? Let me know. Yeah, please just say it, yes or no. I'm sorry. The reason is because I have to click again to see if you say yes or no. Okay, thanks. Thank you, Kelly. Yeah, exactly. It's negative, right? Do you think the answer is pretty reasonable? Yeah, your expected value, your expected profit when you go to casino, play a specific game, you are expecting to lose. Okay? Averagely speaking, yeah. Or in the long run. I'm not saying you must lose in one trial. You know, the other day you might get a jackpot. It's possible. I'm just saying, averagely speaking, in the long run, each game you are expecting to lose $1.07. Yeah, if we round to the nearest cents because it's money, right? It's negative 1.07. Yeah, be careful with the rounding. Is that clear? I just show you. Yeah. If you know where to find the recording, watch this part. How do we find the expected value of a discrete random variable? By constructing the probability distribution table. Also, those two columns is to help us to set up the process. Yeah, those are also important. Even those two orange columns are not part of the probability distribution table, but they help you to find the expected value. Again, what is expected value? Is the mean, the average, the typical value you're expecting to have if you try one time of the procedure. Okay. Okay, we only have 13 minutes for the second session. Let me make sure we are good with this section. I think we're good with this section. So let's move to the next section. Binomial. 5.2. Okay. Binomial distribution is a specific discrete random variable. So this is a notation, okay? I'm going to spend time to explain what is binomial distribution. What is binomial distribution? Binomial distribution refers to a procedure the procedure satisfies the following a few conditions. Number one, it has a fixed number of trials. The number of trials, we use n. Yeah, we use n to represent the number of trials. Okay? Yeah, the parameter, this is the parameter of the binomial distribution table. N here is the number of trials in the procedure. Yeah, for example, you toss a coin 10 times, then 10 is going to be the value of n. For another example, you roll a die, how many times? 20 times, then 20 would be the value of n. Okay, so that's the first condition. Your procedure, your probability experiment contains n trials, and n is a fixed number. It doesn't change. Yeah. Number two, the n trials are independent. Independent. Okay. So my two examples earlier satisfy this condition. You toss a coin 10 times, that's 10 trials, and those 10 trials are independent, right? It doesn't affect each other. And then if you roll a die 20 times, and those 20 trials are independent. And in this section, we're going to see a 5% guidance. Today, when I meet up Kelly, right, I mentioned we have a 5% guidance. And we do have cases in which the trials are not actually strictly independent, but to avoid troublesome calculation, and we assume or pretend those trials are independent as long as the number of trials compare with the number of values in the sample. Yeah, if it's only less than or equal to 5%, then we pretend is independent. Okay, we don't have to go over that now today. Just saying we have something like that. Okay, yeah. The second condition is the n trials are independent. The third condition is each trial, the outcomes of each trials can be divided into two categories, either success or failure. Okay, yeah, for example, you roll a die. That's one trial, right? Yeah, I know we have 6 different outcomes. Number 1, number 2, number 3, number 4, number 5, number 6. But if you let getting a number 6 as a success, then all other numbers, 1, 2, 3, 4, 5, they are failure. So we are able to classify all the possible outcomes into two categories. Yeah, one category is a success, the other category is a failure. All right, yeah, we can do that. Yeah, for example, if you toss a coin, if you let being getting a head as success, then getting a tail would be failure, right? And you know what? The probability here, P here, is the probability of success. Yeah, success. SUCC. Okay. So, and the last condition is the probability of success remains the same for all n trials. Yeah. So if we roll a die 20 times, each trial, if we let success be getting number 6, then the probability of getting number 6 each trial remains the same. It's always 1/6, right? It doesn't change. Yeah, that's very important as well. So if we have a procedure, the procedure satisfies the following 4 conditions, then the procedure is a what? Binomial distribution. Okay? The procedure is a binomial distribution. 2 very, very important parameters about a random variable. Here is a discrete random variable that satisfy or binomial distributed are n and p. N here is the number of trials. P here is the probability of success. All right, let me give you an example. So far so good, guys? The concept-wise, we have 7 minutes. We're gonna hurry up, okay? So let me give you an example. To save time, let's consider rolling a die. How many times? Let's just do 10 times, okay? Yeah, 10 times. And success, you can let success be getting number 1. I'm just, getting number 6 because Chinese people like number 6 means lucky, right? Okay, then your failure would be getting other numbers, right? Yeah, what is the probability of getting number 6? What the probability of getting being success? This is lower p, okay? Yeah, the how do we handwrite lower p? This is how do we handwrite lower p. Lower p represents the probability of success is going to be 1/6. All right, guys? Then we use Q. What is Q? Q is the probability of failure. And what's the probability not getting a 6? Yeah, P plus Q must be 1, right? P and Q must add up to 1 for sure. You either success or you either failure, right? Okay, so now I'm gonna set up the probability distribution table for X. And what is X? X is the number of successes. Always like that, okay? For binomial distribution, the random variable X, when we say this random variable X is a binomial, followed binomial distribution, or binomial distributed, that X always represents the number of successes in the n trials. In our case, X represents the number of successes in the 10 trials. Okay, 10 trials. Okay, let me set up the probability distribution table for X. 2 column, capital X. The first column, we're going to have all the possible value for X. And second column are going to be their probability. Okay, so what do you think? What are all the possible values for X? Could X be 0? Could X be 0? Among the 10 trials, we
no,
don't
it's 1, 2, 3, 4, 5, 6.
We cannot get a 0? Can we get a 0 though?
No, not for dice.
Okay, let me repeat. X here represents the number of successes among the 10 trials. When we roll a die 10 times, right? X represents the number of 6 we got among the 10 trials. Is it possible we don't get any 6 at all?
Yes, so it's
that's
going to be
possible.
0 to 10.
Yeah, 0, right? So it's possible we get a 0, right? Okay, so and then it's possible we get a 1 success among the 10 trial, or 2 success and 10 trial. Yeah, why did I choose 10? So many. 5, 6, 7, almost 8, 9, 10. No more than 10, right? In the luckiest, all the 10 trials you get number 6. Okay, that's gonna have a lower probability, but it's possible. So all the possible values for x are 0, 1, 2, 3, all the way to 10. So we're good with the first column, all right? So let me show you how do we find their corresponding probability. What's the probability that among the 10 trials, we do not have any success? All the 10 trials are failure. First time failure, second time failure, all the 10 times failure. So do you think the probability is q to the power 10 by the multiplication rule? Yes or no? First time failure, second time failure, third time failure, the 10th time also failure. Does that give us q to the power 10? Q is the probability of failure.
So that would be correct, Q of 10.
Yeah, right? Q to the 10, right? Yeah, in this case, it's a 5 or 6 to the power 10, right? Right? Okay.
Yes.
So that, yeah, okay, perfect. And now let's move to the next row. And what's the probability that x assume 1? Let me slow down. It's okay if we don't finish. We're going to continue on Thursday. Even I really need to finish that. So what's the probability of x equals 1? Let me specify this. Probability of x equals 1 means among the 10 trials, we have exactly 1 success and 9 failures among the 10 trials, right? Okay, then do we know which time we got a success? Do we have to have the first time success, or the only time success could be happen the first time, first trial, or second trial? Yeah,
it could be at any time.
Yes, exactly. Very good. So that's how do we have a C10-1. Yeah, what is C10-1? Combination. So in order for that to happen, we need to firstly pick a trial to assign that trial as a success. We have 10 trials, so from the 10 trials, we pick 1, and we're gonna use that 1 trial as the only time that success is gonna happen. Do you see what I'm talking about? Yes or no? So we have 10 possibilities. 10. The only success could happen the first time, could happen the second time, could be the third time, and could be the last time. So that's why we have C10-1. That's equal to 10. Okay, and now we know which trial is success, right? So the probability is P, and we know all other 9 trials are failure. So we have Q to the power 9. Try to digest that. Yeah, try to understand that. Does that make any sense? Try to use the multiplication accounting rule. I know it's not exactly, but that's the theory in the back support this formula. So we firstly pick a trial among the 10 trials, and we let that trial has success, and all other 9 trials as failure. So the probability of x equals 1, the probability that exactly 1 success and 9 failures among the 10 trials is going to be C10-1 times P times Q to the power 9. C10-1 times P times q to the power of 9. I want you to try to understand that. Yes or no?
Yes, it makes sense.
Okay, perfect. Awesome. Yeah. Now what happened to x equals 2? What's the probability of x equals 2? X equals 2 means among the 10 trials, we have exactly 2 success, 8 failures. And which 2 trials gonna be success? We don't know, right? Any 2 trials could be. So that gives us this formula. We firstly pick 2 trials from the 10 trials. It could be the first 2, or the last 2, or the middle 2, or any 2 times 2 trials of the 10 trials. And now we have 2 trials picked, all right? And we are going to give that 2 trials successes. So P times P, P squared. And then the other 8 trials, they are failure. So we have Q times Q times Q times Q times Q times Q times Q. So Q to the power 8th. So the probability of getting exactly 2 successes is C10 P to the power 2, Q to the power 8. Yes or no?
Yes, it makes sense.
It makes sense.
Okay, so can you help me to find a formula for finding probability of x equals 5? So we should have 10 C10 5, P to the 5, Q to the power 5, right? And this one should be C10 7, P to the 7, Q to the 3, right? 7 times success is 3 times failure. And this one should be C10 9, 1 success. Hold on. 9 success, 1 failure. And this one would be C10 10. Actually, we don't have to be C10 10. C10 10 is just 1. So we have 10 failures. 10 successes, my bad. So we have P to the power 10. This is a Q to the power 10, right? Yeah. This is a P to the power 10. And that's how do we understand the binomial distribution table. Can we use a calculator, TID for calculator, to find those probabilities and the mean and the standard deviation? Yes, but we run out of time. I'm going to show you the very beginning of Thursday. Okay, so if you you don't have to do 5.2 before Thursday, all right? Yeah, you're going to do that after Thursday. Yeah, we plan to finish that, but we didn't. We ran out of time. I'll show you how do we use a calculator to get that done. Then you don't have to struggle. Yeah, this is a tons of calculation. This tons of calculation. So we'd like to use a calculator. All right, guys. So that's for today. We're gonna continue on Thursday. Let me take a picture of the attendance. Yeah, you need to know that I take attendance in the beginning and in the end. So please do not rush to leave before I say, let me take attendance and say good night. All right, guys. Thank you guys for coming. You guys have a good night. I'll see you on Thursday.